try to make an overview. Let's see where we are going. So this is the outline of the, let's say, next 45 minutes, and I'm talking about geoelectrics, so ERT, and Pritam is going to take over for all the electromagnetic induction stuff. Obviously, starting with the introduction, and the second part, I think it's pretty interesting and pretty good to know is talking about what are the physical processes behind conduction at all, to understand what we are measuring and how to get information about the subsurface and freshwater differentiation to saline water. Then just very briefly, equations, and then stepping into measurement principles and inversion, which is a necessary topic to talk about. And I'm going to end with at least 3 examples, including also some devices. So, introduction. I promise that there will be pictures, not always only text and symbols. But so what we are talking about is that electrical conductivity, so sigma, is a way of measuring the ability of a material to conduct current. That's the basic principle, and the parameter that impacts this is electrical resistivity or conductivity, and they are just the inverse of each other. Sometimes I'm using conductivity whenever I'm talking to a hydrologist. I'm using conductivities, and whenever talking to geophysicists, then I'm talking about resistivity. Sometimes I mix it up, and everyone gets confused. And anyway, so the unit for conductivity is Siemens per meter, and resistivity is an ohm meter. Just to make this clear. The nice thing about conductivity is it really spans a large range of values. That's what is shown here. This is not only, no, it's not at all geological material. It's just what we have on materials on Earth overall, but it's good to know. So we are talking of 10 to the power of 18 when talking about diamonds, but very close to it's quartz, and I mean, that's something we are dealing with. So it's 10 to the power of 17. And we can go down like water, then we are ice, still pretty much a non-conductor, but water has on its own a spread. I'm talking about that later. So when we say saline water, then we are talking about 0.2, and if it's a destillated water, it's 10 to the power 4. So then it's a spread on its own. But going to metal conductors, like copper is one of them, then it's 10 to the power of -8. So it's a spread of 26 decades. That's really amazing still, I think. And we separate them between, conductors. It's all the material that conducts current, up to insulators, and minerals are somewhere in between. Okay, so what causes this conduction? These are basically 3 things that we have to distinguish. The first thing is metallic conduction, and that is where the movement of free electrons in this conductive material. That's what I'm talking about, metals. Like the copper case, they have really electrons flowing in the material, transporting the charge. Sorry. Okay, thanks. The second thing is electrolytic conduction, which is also transporting charge, but not by free electrons, but by ions in a fluid. That's already a difference, and that's what we mostly will talk about. So this is the more important thing for us, because it's the ions which are solved, for instance, in water, and makes the water saline and being able to transport charge. And the third case is surface conduction. I'm going to come back to this later. This is more important when we have an interface between fluids and the grains, something we're going to have. We can come back to this point when talking about clays in just more or less a minute. So keeping these 3 in mind, mostly talking about electrolytic conduction. And what I've shown here is the spread we can have in water with changing ion concentration. So this is ion concentration in milligram chloride per liter. This is 10 to the power of 2, going up to 10 to the power of 4. So this is basically fresh water here, and this is seawater. And on the y-axis here we have conductivity, Also nice, it's in microsiemens per centimeter. That's the common unit we have for the hydrologists. And then this is, let's see, 10 to the power of 2. So it's 100. It's like 300 microsiemens per centimeter. That's fresh water. And if we have a solution to seawater, then we go up here, and it's like more or less between 4 and 5 10 to the power of 4. So it's spread on its own like two decades, a bit more than 2 decades between fresh water and saline water. But that's just the fluid conductivity. And typically we have the fluid in some material, and that's why geophysics, it's not measuring the fluid conductivity. That's probably the most important thing to remember from these early slides. So this is electrolytic conductivity and surface conduction. So surface conductivity is whenever ions are moving at this interface between fluid and solid. So then we have a potential drop. Some of the electrodes are bounded to the surface, and some others can move in the fluid. And when we apply a current, then they will separate. And if we shut off the current, they will move again and scatter. So don't get too much into detail. Just remember we have metallic conduction, electrolytic conduction, and surface conduction. It will become important at some point. And that was the slide that I wanted to go to. What we have as a geological material is a mixture. I was just talking about the water in this pore space here, so there and there and there. But there's not only water that we are measuring. There might be grains. You remember quartz? There might be organic matter. There might be clay. So we have a mixture of different components that we are measuring all together. So we are not just sucking the water out of a well and measuring the conductivity of this water. We are measuring with geophysics this more or less. No, it's not more or less. It's a complex system which can be composed of different things. I forgot there may be also air in it. Maybe not in a marine, saturated environment. But if you do it on land, you can also have a desaturation. So it's a mixture of complex components. So what do we do with this? And for the next slices, we, in our case, typically ignore the metallic conduction because we are not looking for ore detection or whatever minerals, at least today here. So that's why we are basically looking into all the two other components. So how do we do this? There is one most important equation that we are looking at, and this is Archie's equation. I'm starting with Waxman-Smith. I'm starting with the complicated one and going to the more easier one later on, but it's easier to start with the Waxman and Smith equation because that handles what describes is this equation down here. This is what we measure. So it's the so-called bulk conductivity, so the complete system, and we describe it being a sum and the product of the porosity to the power of m and the fluid conductivity. So fluid conductivity is our water in the pores. It has a certain conductivity, and that's multiplied with how much space it is filling up. So that's porosity. And then there's one more term here. This is m, which we call a cementation exponent. Because just imagine you have a block and a certain volume that is saturated in this block, but no connection from this inner fluid-filled volume to anything else. Then it would still be an isolator if you're measuring from outside, at least with the electrical methods. So you need to have a connection between the different water components. So the current needs to flow somewhere here, going there, whatever. If there's no connection, then I would not have conductivity. And this is what is covered by this so-called cementation exponent. So this is all what comes from the ionic conductivity. And then we have the surface conductivity. And that's what I mentioned before. Whenever there is some ions attached to the surface of the grains, we have the the so-called surface conductivity, and all together gives us the bulk conductivity. So we are describing saturated sediments by this electrolytic and surface conductivity. And the reason why we do this so simple is basically we think of them in an electronic way to put them in series. Sometimes it's working, sometimes not. So this is the surface conductivity is one component, and it's in series with the electronic component, and that's why we take them just as a sum. What else can we know about it? We also can just now in thinking about what happens if we change the fluid conductivity, which might be the more important part of these two components. And therefore, look at this graph here. This is the fluid conductivity. Here, the fluid conductivity is low, and here is it high. What is more important in this part? If this becomes high, this term becomes high and is outplaying the second term. And this is I'm pointing to this because in a marine environment, fluid conductivity is typically high because of the saline water. And if this fluid conductivity is high, this term is high, and this guy is comparably low. And that means most of the times when we are thinking about measuring salinity in marine environments, we can concentrate on this term and forget about the second one. So then this is like more or less on what I said already. It's just giving a name to the variables. So bulk conductivity, porosity, sedimentation exponent, that's the things that I already explained. So if we now forget about surface conductivity for the moment, then a typical way, if I don't want to know explicitly about porosity and cementation exponent, sometimes you're going to find equations that just shorten them to this F, which is the formation factor, which is something RG typically or does initially to name this formation factor, which holds porosity and cementation component. This is something you maybe easily get by measuring the bulk conductivity and measuring the fluid conductivity. It is more complicated to really know about cementation form factor and really know about porosity, but it might be much easier to get this factor without diving too deep into distinguishing these two. Yeah, I wanted to give a number. So formation factor, just to give you an idea, is typically for loose sediments, it's somewhere between, let's say, 3 and 10, just to have a rough idea of what I'm talking about. So meaning if I have a fluid conductivity of seawater, then the bulk conductivity is, let's say, 3 times higher than seawater. This gives now some graphs for this formation factor. Yeah, talking about between 2 and 5, and the cementation factor, depending on the material we are talking about, is somewhere between 1 and 2 for loose sediments. Can be much higher for sandstone and compact sediments. But I guess, yeah, when we're talking about loose sediments, we are good with, let's say, something 1.3, 1.4. That's what at least I, in our studies, typically assume as a cementation factor is 1.3 if I don't know anything else better. Okay, now I promised an example just to give you an idea. This is the same sand. So I took a sand of a porosity of 35% and a cementation factor of 1.3. And then I put fresh water from this graph we have been talking about, 3 times 10 to the power of 2. And if I just do the math, then I'm ending up with a bulk resistivity of 130 ohm meter. So if I have sand with fresh water, just to give you some numbers, we are typically talking about, let's say, 100 to 200 ohm meter. Then I have fresh water in sand. Now I have the same sand, still the same porosity, same cementation factor, but just changing the conductivity of my fluid. So 10 to the power of 4. Then this ends up to an ohm meter. And this is quite nice because that tells us, okay, we have almost 2 decades between freshwater and saline water saturated sand. So that's a good contrast to be measured. Surface conductivity is always 0 at that point. But what happens if I'm now taking the freshwater? I'm taking the freshwater. So this is all the same numbers, but now I am adding a surface conductivity. This is just it's just a number that I put in. It's not totally far off. It's quite okay. So 10 to the power 3 Siemens meter per centimeter. So we have freshwater saturated sand, but put in some clay. So sand clay mixture, and then we are getting to a value of 10 ohm meters. And that's actually the complication you may have if you're working in marine environments. Especially when talking about saline intrusion, then it's hard to distinguish whether I have saline water in my sediments or do I have clay. So even though I mentioned mostly we can neglect the surface conductivity, if it's fresh water in the sand, but I do have clay, then it may appear as I have a sand material with some brackish water. So that's something we cannot solve by geoelectrical methods alone by these conductivity values. That's always something to keep in mind. Okay. Well, then I started with the overall material on Earth for conductivity. So going now to geological materials, it's still quite a reasonable spread. 10 to the power of 5 to 10 to the power of minus 5. So it's still 10 decades, and we are it's fresh granite. It's 1,000 ohm meters. Gravel saturated, it's still something like 100 to 1,000 ohm meters. Clays, we have an ohm meter, maybe up to 100 ohm meters, and depending a lot, and that's what I have shown before, depending a lot, obviously, on the water saturation. So the more water you have in your material, the more conductive it is typically. So there are 2 factors controlling our bulk resistivity. It's the salinity in the of the fluid itself, but it's also the amount of water we have in. It's the porosity. So if we have less porosity, obviously we have higher resistivity. So it's the amount of water, how it is connected, and how saline this water is. These are the two players in that game. And then, of course, it's a bit the rock type that we have to figure that out. So the spread is large, but we do also have some overlapping. But this, for the moment, maybe not that most important for us because it's controlled by the salinity of the pore water. Okay, so this has been what we call the petrophysics. So knowing from our measurement of resistivity to the parameter we are probably mostly interested. So the pore water conductivity or salinity. I guess for us that's the more important parameter. When it comes to how to measure it and how to set up the whole thing, making this a bit more quick. So of course there's some math behind. I could have written here Maxwell's equation. I'm going down to Poisson equation. So this is the equation describing how the current is distributed and flowing in the subsurface. So here goes in the conductivity. Here's our source term. So this is how we inject current, and this is basically the measurement. And if you do it very, very simple and have just a single electrode, then these are the current lines, the way the current flows into the ground, and the potential forms these kind of hemispheres. And if we simply now changing the resistivity, you may get graphs like that showing you how the potential that I measure, so injecting current, some current here, the conductivity is impacting on the voltage, and the voltage is that what we measure, and you can get graphs like this. And the point that is important here, the voltage that I measure depends on the distance to my injection point. So if I take the injection point and measure the voltage somewhere, I can calculate the resistivity in between. And it follows basically this very simple equation. And that was for homogeneous half space. There I have just hemispheres. If I now go to a layered case, it looks a bit different. But the good thing about is that's what we calculate, and if we measure, we can get the ground from that. So this is 100 ohm meter over it's 1000 ohm meter above 100 ohm meter, and here we have vice versa, 100 ohm meter above 1000 ohm meter. And what we see here is that the current lines, they do have some dipping at this interface. And this is not only at the interface; it has a relevance also on the surface here. So if I measure at this surface my potentials, so these are the potential lines in this colors here, and if I measure them, I will get not only an information of this first layer, but also something about the second layer. And that's the general idea behind geoelectrics, that if I have an electrode and the further I go away from this, I'm sensing deeper. The further I go away, the deeper I sense. Also, always tell is we are not using just single electrodes for several reasons. The most important reason is that I want to avoid contact resistance. Just imagine if I have two electrodes, stick them into the ground, and I want to inject also current and measuring potentials, then I have two things that I measure. I measure the ground, and I measure the contact resistance between the electrodes and the ground. And this contact resistance can be much higher than anything else. So that's why I'm using 4 electrodes. 2 electrodes for injecting current, and then and 2 other electrodes to measure the potential. And measuring the potentials is avoiding contact resistance, because there's no current flowing by measuring this. So that's why if you are asking or wondering why we use four electrodes, that's the reason for these 4 electrodes. And this can be relatively easy calculated. It's, potentials can be superimposed, and then I have to do the math for these 4 electrodes. Don't let me go into details there. But what is important, and you may come around, is the so-called configuration factor. So for those who have maybe measured some geoelectrics at some point, then you will realize people talking about configuration factors. And this configuration factor is essentially the geometry of your electrode configuration. It just gets in all the positions and the relative position to each other's, so that by the ratio of voltage to current, are then getting the resistivity of the ground. Here I get a small subscript of A, which is named for apparent resistivity, because this resistivity that you can calculate by the ratio would be only the true resistivity if it's a homogeneous half space. How to get from apparent resistivities to the true subsurface, we come there in a minute. Okay, there are some different setups of these 4 electrodes. The most important ones are these 3 you see here, and you may have realized the names of them. Maybe the most important to distinguish them, sometimes for these 2, you have your current electrodes. The current electrodes are A and B. They are outside, and potential electrodes are inside. So it's like a stacked array. So current goes here, voltage goes there. For this Schlumberger array, which I also come back later to this, you stay fixed with this voltage electrodes and you move the current electrodes. It's more or less done for soundings, and it becomes important later on. Venn array is more or less the same, but distances between all the electrodes are always equal. And then there's one setup which is called dipole-dipole, and the name basically comes from the fact that we are separating our voltage dipole from our measurement dipole. So these are the three most important arrays. I will later on talking about so-called inverse array. This is nothing else than I'm switching the current electrodes from outside to inside, and the potential electrodes are outside. This in theory would give you this exact the same measurement value. So this is what we call reciprocity. It has one key advantage. I'm coming back to this at the examples just to have this in mind. I can switch from inside to outside. So if you do this on land, you can have a lot of electrodes laying around. All these red boxes here are electrodes, and you have an instrument which can connect by a multi-cable to all of those, and then just measuring them and sitting right beside it, the field, waiting for the measurement to be done. So it means having 2 and 3D arrays that you can do. So I was talking about apparent resistivities, and you will sometimes realize the name a pseudo section if you do ERT measurements. I just want to quickly point on how this so-called pseudo section come along. So if I start with one of those 4-point configuration, this is like this Venner configuration, all is equal, and then I'm going across a line. So I'm moving this 4-point from one to the next, so going on the ground. Having always 4 electrodes measuring. And what I do then to go deeper is I'm just increasing the distance between those electrodes. So twice the distance, meaning I'm going deeper, and I'm doing the same again. Okay? And I can continue this as long as I'm reaching the whole profile. And that means I'm getting all these measurements for different separations. So this is first separation, second separation, third separation. There would be a 4th separation, and the 5th and the 6th. And the 6th means that my first electrode is here, current-wise, the last one is here. And this is now filled with colors. So just a colored image of my measured values, and that's what you see here. Is that what we call pseudo section? So that's our measurement values just by a nice representation. This is not our subsurface. That's something I want to point it out. Whenever you see pseudo sections, it's not your subsurface. It's just measured values. And as I showed before in these easy pictures, it's the whole subsurface is impacting your measurement value. It's not responsible for a certain block in the subsurface. It's always impacted by the whole subsurface. And that's why, so this point not stands for a certain depth somewhere here, it's impacted by a certain area. And to resolve this, we need to do what we call inversion. And that's maybe an easy to get example. This is how data could look like. And this is the subsurface that belongs to this. So this should tell you, okay, this is, just take it as data and not trying to get the image of the subsurface from your data. And this is, we need to go from here to there. So this the subsurface image we need to get from the measured data. And this is true for all the potential field geophysics. And this is what we call inversion. And if it's more on an abstract way, you have a connection between your data space and your model space. That's just the image in between, or it's just a function in between. And that function in between is described or governed by all the equation, by this Poisson equation. What is important at that point comes at this slide. There is almost at all time less data than 3 parameters in the subsurface. And also, this data is not perfect, it's noisy. And if you take these two together from the just inverse theory, you were going to learn, okay, this solution can only be non-unique, meaning there is not only a single solution from your data that you can get. Also something to keep in mind. Whenever you get an image from a geophysicist, this is one of the possible solutions. There are more. And he may give you an idea of that by having other solutions or giving you some uncertainties. But keep in mind, there's always more than one solution. We try to stabilize this inversion, and we do this by what we call additional constraints. So some ideas of how a solution should be or could be. And then we put it into what we call regularization. So there are assumptions, and these assumptions make it possible to have a solution to this inverse problem. So one of the few equations, if you write it down, basically what you solve is a so-called minimization problem. And this holds now how to come from, let's say, the model I have that generates some synthetic data, and we compare it to the measured data. And then we change our model as long or so long that these synthetic data from the subsurface matches the measured data. Okay. But as I said, this is unstable. We have this additional term of regularization. And for instance, this can hold just what we call smoothness. So we say, okay, the model I'm thinking of should be somehow smooth. It should not have abrupt changes. And this gives additional information to the inversion process and stabilize it. And to give you an idea of what or how this could impact your inversion result, I'm showing you from the same data set. So this is this data set here. And changing this parameter, who somehow regularizing, okay, do I have a look on my data or do I more have a look on my smoothness? You may end up with these different images. I mean, they do have some similarity, of course. But here there's much more structure in, and it gets smoother and smoother because I'm driving my solution to be smooth. And that's what the regularization parameter is doing. But we have a little bit of an idea how to control this. What you see here is the mismatch or the match between measured data and synthetic data. And they, of course, should somehow be similar. So this is the misfit. So this should be kind of, let's say, random looking like, because that's what I have on my data, some random noise. So if someone comes along with a result like this, you can ask him, okay, how does your data fit look like? And then he needs to answer you, okay, I'm missing or I'm fitting my data within the uncertainties of the data. This would not be the case here because there is structure in the misfit. You know, there's some structure there which says, okay, there's some data I cannot explain by my forward model. These two here are more random-like looking. Still, there is a little bit in there, but compared to this, it looks like I have a random distribution. And then I'm stuck with these two images, and then I have to decide, okay, do I prefer some smoothness or do I prefer not smoothness? That's always a bit of a discussion. There are ways to come around to discuss this, but this would go a little bit too far. Okay, examples. Going through 3 examples. The one is directly at the beach. It's at the beach of Spiekeroog. So we are not talking about really marine measurements. We are talking about measurements at the beach. What we are investigating here, these so-called apostolline plumes, which occur if you have the tide movement from the ocean to the beach, which puts salt water on the beach, and on the other hand, you have fresh water, which is building up the outflow of the fresh water. So that's why the salt water is sitting on top of this fresh water. This is how it looks in theory and for, let's say, normal beaches with a certain slope. And in this case, we were looking about, okay, what's going to happen if this beach is with a certain topography, and a certain topography that always also changes over time, if there are some storm floods coming and changing this behavior. And then you have a situation where this apostolline plume is not just a single plume, but maybe a bit more complicated. And this is where we did a lot of geophysics. This is the beach at Spiekeroog, like 5 years ago, I guess. So we went there every 6 weeks over the last 3 years, so a couple of campaigns. And we installed a monitoring well just in the middle of the profile with electrodes buried in the beach 20 meters deep. What you get out is something like this, starting in September 22 to December 23. This is where the dunes are. So blue is fresh water. So what we made the last years is here an inversion which really goes for the salinity. So we are putting this formation factor stuff in it, and also temperature we put also in it. Maybe not too important at the moment. So blue is fresh water, and here are the dunes, and low water line is where the sea is. All the profiles have different lengths because it's not always easy to make a whole measurement during the tides. They are coming like every six hours, and measurement takes a bit of time. So you have to scatter your things a bit, and also the beach is changing in its topography. Sometimes it's just not possible to make long measurements. So what I wanted to show here is have a look at this area here for the moment. So this is where the freshwater comes. Typically, high water line is here, but there are winter storm floods. And if you look between December and March here, in the winter time, you had a strong storm flood over this high water line, which puts a lot of saline water into the upper beach. And then we can monitor from August, October to December how this saltwater front is slowly diluting in this fresh water, and then there comes another smaller storm floods here. So that's something you can nicely do with Geoelectrics as an example. And you also see that somewhere you have this freshwater discharge tube. So that's that guy who pushes the freshwater into the sea back. And you see with the time, this upper saline plume is deepening a little bit here, and freshwater is coming out earlier to the sea. So here there's almost freshwater comes somewhere here, but it goes closer to the beach. I could give you another talk on why this is and what happened to the beach, but I just want to show you some numerical modeling from the hydrogeologists. So the density-driven hydraulic modeling based only on these 4 monitoring wells. So they have salinity there and they have hydraulic heads there. Just a common modeling. And if you compare what you get in geophysics and from this modeling, you get quite similar results. So another task to do is to put this data into this modeling, but it's some future. So using Geoelectrics, you can get quite good imaging of a salinity distribution. In this case, at the beach. So how does it look in marine environments? I found two papers, and first of all, I want to point out at this image here because this brings me back to the electrode configuration, and that's the more common one in marine measurements. This is basically what we call a Schlumberger or an inverse Schlumberger array. So you have the potential the current electrodes in the middle. So this is A and B, and then you have the potential electrodes. And the reason why you do this inverse is you can do these measurements simultaneously. So you have your current injection here, and you can measure a lot of potentials at the very same time. So this just depends on the instrument they have. They were using a Cisco Deep Marine system, and I think it has 10 simultaneously potential measurements. So 10 channels who are measuring the potentials while injecting current. So that means you're getting kind of a sounding at every second that you do the measurement. And in this case, they had like 195 meter long floating cable with 10 meter spacing. So the spacing between A, B, and all these electrodes is always 15 meter. And that's also interesting to know. The injection current is quite high. So we are talking about 35 to 50 ampere injection current. So then you do a measurement, and if you continuously drive with your boat, and take the streamer behind you, then you always make this kind of soundings, and they just go one after another. If you're thinking of this pseudo section that I showed you, that would be a line in depth. You know, you had this triangle, so that would be at one point a line in depth, that one another. Okay. What I want to show here, basically, it's the same setting. Actually, it's one of those beaches we will go in the future. But what they did, they both did measurements on land. So these are the KO and K1 profiles here in red. But then they make measurements, marine measurements with the system I showed you just a slide before, during low tide and during high tide. And these are the three profiles that are stitched together. So this is on land ERT, this is marine ERT, and this is marine ERT, high tide and low tide. And I hope, especially for these, take a look at these three here. There's something you can immediately see. Taking the measurement at the beach with just electrodes sticked into the ground, no salt water on top of it, you get much better depth penetration. Here you have this floating system. In gray is the marine layer, and the depth of penetration is dramatically reduced. Like it's maybe 15 meters here, while here you can go down to 30 meters. This marine layer is sucking most of your current of a DC geoelectrics. It's truly hard to get any kind of current into the sediments. And that's what you very nicely can see here. Still, you get quite some information. So it's the same setup that I described. This is the upper saline plume. This is the freshwater discharge tube. And you see this discharge tube also from this marine measurements here. So there is some information, but it's really more difficult to get. A second example, and another instrument that has been built by the Kiel University, or at least the idea came from Kiel University. They are using a RESEX. The length of the streamer is pretty much similar, so it's 200-meter floating cable. But the setup is a little bit different. It is still this inverse or reciprocal Schlumberger array. So you have current in the middle and potential field readings outside. But what they do is they increase the spacing, and this is a very clever way of doing it, because if I have just equiconstant spacings between my readings, like before 15 meters, now I'm starting with a more or less logarithmic spacing. I'm starting with small distance, and I'm making them far more spread out. The advantage is I'm getting better resolution in the nearer part when I have dense readings of electrodes. That's why they did this. This is a typical setup that you do for so-called Schlumberger soundings, even inland. There you start with smaller electrode distances and you increase the distance. This is a very natural way of doing it. And the RESEX is a system which allows you to use much less current, but the accuracy of the potential field readings is much better than for sysclotters. And these are one of those results you can get from. I guess that's a bay in Turkey. What is nice to see here is they made at the beach, they made TEM profiles. This is B, which has a certain penetration. They made frequency domain EM, which is looking not that deep, but gets really nice and high resolution along the beach. So this is this green line here is A, the magenta one is B, and then there are 3 ERT lines, C, D, and E, further away from the beach. And what we see here and what we learn is, on the one side, in green, this is low resistivity or high conductivity, so that's salt water in infiltration. So stream 1, stream 2, maybe that's good to have a look. So it's stream 1, it's here, relatively resistive. So that's the freshwater. Stream 2 is the freshwater. So somewhere in between stream 1 and stream 2, we have this low resistivity anomaly, which is saline intrusion into the beach somewhere here. And if we have a look at this marine measurements, then you see these anomalies here, which pointing into, let's say, resistivities of 20, maybe 30 meters. And this is obviously less saline water in the subsurface below there, somewhere here in that area. And if you are looking at this measurement of the salinity of the seawater body in PSU, and you see this drop from saline water somewhere low. It's not a lot, but you can see it, and that tells you also there must be some discharge at this point. And that coincides quite well with what we see in the subsurface. You have something like between 5 and 10 meter water depth here, and looking like 30 meters into the subsurface. You also see the deeper it gets, that the more complicated it gets to get any results of this. Okay, and that's from my side.